Okay, guys, here we are back for the final installment for Unit 7, in terms of lectures and notes at least. And we're going to talk about now that we know how to do Lewis structures and we know how to assign formal charges and where to put the lone pairs and where to put the bonds and how to identify things like that. We're going to talk about molecular geometry, which is essentially referring to the various shapes we get from our basic Lewis structures, okay? And in order to be able to correctly identify our molecular geometry, we first need to be able to differentiate between what's called an electron region versus a bonding region versus a lone pair region, all right? It's fairly intuitive, but there are a couple things worth clarifying, okay? So, first of all, the number of electron regions will range from 1 to 4, at least for the molecules that we draw, okay? And it refers to the number of locations around the central atom in which electrons are found, all right? So, a single, a double, or triple bond counts as one electron region, right? It's on one side of the atom is maybe the way you could think of it. All right, so it's the number of areas or the number of sides in which you find electrons. All right, but a lone pair also counts as an electron region. So if you take, for example, the ammonia molecule, right? I have 1, 2, 3 locations with bonds and 1 location with a lone pair, right? So that amounts to 1, 2, 3, 4 electron regions. Okay, if we look at HCN here, so hydrogen cyanide or cyanic acid, hydrocyanic acid, we see 1 bond there and we see a triple bond there. So remember, a single, double, or triple bond counts as 1 region. So that's 1 region, that's 1 region. So this one has 2 electron regions. Now, notice we are not counting the outer atoms. We're only looking at the number of electron regions around the central atom, which would be nitrogen in this case and carbon in that case. Okay? And so we're not counting that lone pair out there. We're only counting the regions around the central atom. So in this case, I have 1 here, 1 there, which makes 2. I have 1, 2, 3, 4 around nitrogen to make 4. All right? So electron regions are anywhere we find electrons. It could be a lone pair or an area where we have bonds. Okay? Now, the number of bonding regions, which again could be anywhere from 1 to 4, refers to the number of locations around the central atom in which bonds are found. Okay? And so a reminder, a single, double, or triple bond counts as 1 region, but lone pairs do not count as a bonding region. So again, we already established that our ammonia molecule has 4 electron regions, all right? But if we want to know the number of bonding regions, we only have 1, 2, 3. We would not count that lone pair. So that'd be 3 bonding regions. Oh man, that's horrible. 3 bonding regions, okay? Whereas the cyanic acid molecule here, or HCN, would have 2 electron regions and 2 bonding regions. 1 there, 1 there. Alright. The VSEPR theory, that stands for valence shell electron pair repulsion theory. Alright? And what this states is that electron regions will spread as far from other regions as possible. Okay? So what they do is they essentially try to maximize the spacing in 3 dimensions, and that affects our bond angle and what we call the shape of our molecule. Alright? And so some examples you guys will get today on your ChemQuest, this is actually a little snapshot of part of the front page here, right, are some of the different types of molecules we've drawn in class in terms of their Lewis structure. Now, I've had the question come up a few times where, sometimes I'll draw things in a straight line, sometimes I'll draw them bent like that, for example, or how do I know when to do that, right? This comes because, I learned molecular geometry a little while ago, all right? A little while, 20 plus years ago maybe. But anyways, so I was able to predict when a molecule should be bent and when it should come out in what we call our linear shape, all right? You guys now will start to see why I was able to predict that. I've committed to memory, essentially, information about when it should be tetrahedral, when it should be trigonal pyramidal, when it should be bent shape. Essentially, that's what you guys will be doing with this lesson, all right? And so the shape, right, this is kind of a cool little graphic because it's got our Lewis structures that we're familiar with, right? We've drawn all these Lewis structures at more than one occasion, as a matter of fact, right? They show then a three-dimensional depiction of what that molecule would look like and where the electrons and electron regions and bonding regions would be, all right? Then they kind of just systematize what a tetrahedral shape has, for example. So we look at the tetrahedral shape, which would be like a methane molecule, right? We should see that there are 4 electron regions, right? 1, 2, 3, 4. There are 4 bonding regions, 1, 2, 3, 4, and 0 lone pairs, right? And so the resulting shape is what we call the tetrahedral shape. So anytime there are 4 bonding regions, 4 electron regions, and no lone pairs, we have a tetrahedral shape. We can predict that shape, right? We could also predict the bond angle would be somewhere near 109.5 degrees. All right? Likewise, for ammonia, right, we have 1, 2, 3 bonding regions. We have 1, 2, 3, 4 electron regions. All right? One of those regions, this guy right here, is a lone pair, all right? And so because we have that lone pair, we get a slightly different shape. Now notice that this part of the molecule looks very similar to that, okay? But because this lone pair is there, there's no extra atom up there, so we get what they call a trigonal pyramidal shape, all right? Now, I'm not going to go through all of these with you because you're going to have them on your sheet tomorrow. I'm just kind of pointing out the stuff that you need to recognize that helps you identify what shape you should have. Right? Now, the other thing that's worth noting here is the bond angle of 106.5 is a little bit less than 109.5, and the reason for that is lone pairs have greater repulsion, okay, than a bonding pair does. Right? So that just means that lone pair pushes a little bit harder away than that bonding pair does, right? And that pushes those a little closer together. So you should be able to notice here, when I have 2 lone pairs, my bond angle goes down to about 104.5, about 5 degrees less than if those were bonding pairs in those locations. All right? So the more lone pairs you have, the smaller your bond angle is going to be. All right? The more electron regions you have, the smaller your bond angle will be. All right, and that's because of that valence shell electron pair repulsion, right? Anywhere we have electrons, they're trying to get as far away from the other electron regions as possible, okay? But the lone pairs tend to push a little harder against other electrons than our bonding pairs do, right? Which is why we see, because all of these have 4 electron regions, right? Notice as we move to more lone pairs, this direction, our bond angle decreases. Okay? Now, when we have fewer than 4 electron regions, right, we tend to get a more 2-dimensional type shape, right? But again, you guys can see the general trend here, right? So here we have 3 electron regions and 3 electron regions. Here, all 3 are bonding. 1, 2, 3 bonding. Whoops. No lone pairs here. We have 2 bonding. 1 lone pair. Notice again, 3 regions. Our angle is larger than when we had 4 regions. But with our lone pair existent there, instead of a bonding pair, notice our angle decreases a little bit. Okay? Now, of course, when we only have 2 electron regions, 2 bond regions, we get that linear shape and we maximize that spacing at 180 degrees. Okay? So, things you're going to need to know for being quiz and test ready. One is Obviously, we have to begin with the correct Lewis structure. Okay, you do not need to draw the three-dimensional shape, but I do want you guys to draw a bent shape rather than linear. Right? I want you to be able to predict when it should be bent, when it should be trigonal, planar, etc. I want you guys spacing out your electron regions as much as you can. Okay? And then, of course, based on what your Lewis structure looks like, you should then be able to predict the name of the shape. Is it trigonal planar, trigonal pyramidal, right? Is it bent? Is it linear? Is it tetrahedral? Right? Those are the 6 shapes I want you guys to remember. And then I'd like you to be able to approximate those bond angles. Now, you do not need to memorize that 2 electron regions in one lobe pair makes a bond angle of 116.8, because that wouldn't necessarily always be true. I want you to be able to approximate our bond angle. Okay? And by approximating that bond angle, we could say that if there are 4 electron regions, right, like we have for these 3, so 4, 4, and 4, we could say we're going to be between 104 and 110 for 4 bonding regions, or 4 electron regions. Okay? For 3 electron regions, we can say we're going to be between 116 and 120. And then obviously for linear, it's 180. Alright, so you need to remember 4 electron regions gives us a range of 104 to 110 degrees for our bond angle. 3 electron regions gives us a range of 116 to 120, depending on the situation. And that 2 will give us 180. Alright, now it's going to take you guys some time to get through all that and start recognizing all these things. Class time will come. I just want you to be aware of what's going to be expected of you on a test or quiz, right? You should be able to draw the correct Lewis structure, space out your electron regions as much as you can in your Lewis structure, which is new. Okay? Then, be able to predict the shape and the bond angle. Alright? And identify how many bonding regions you have, how many electron regions you have, etc. Alright. That is it for today. You guys will be getting the ChemQuest relatively soon. To help you begin making sense of this stuff. All right?